So here's an example, right, of what is going to happen to you if you only have one receptor, right? So if you only have one receptor, and I shine two different lights, in your receptive field, right, where this receptor lives. Let's say I shine one at 480 nanometers and another one at 600 nanometers. All you're going to perceive are different intensities, really of the same color, right? So if I'm shining it at 480, you're only going to light that receptor up about 10%. And if I'm shining it at 600 nanometers, you're only going to light that receptor up at 5%. So the only thing you're going to perceive there is a gradual brightening in the intensity of the receptor, of the perception that you see. The maximum intensity is going to happen right about here, which I guess is roughly what 500-ish nanometers, right about there. That's where you're going to see that color maximally bright. But at 480 or 600, it's going to be much less intense. All right, so here's another experiment demonstrating what you would perceive with a single, what happens with a single receptor, right? If you, let's say for example, you only had one receptor to detect one color. So in this experiment, what we've got is over on the right hand side, you have two lights shining two different frequencies, 480 nanometers and 600 nanometers, and they're both shooting 1,000. For the sake of this demonstration, let's say that we can shoot exactly 1,000 photons of light into the eye. So, as you know, a photon is the little particle that is light, and it travels kind of as a wave and kind of as a field, right? But it travels like this, and at a certain frequency, right? Either 400, in this example, either 480 or 600 nanometers. So we're shooting these two lights into the eye, and we're shooting 1,000 photons of each wavelength into the eye. Over on the other side, we're in the left-hand side, at the top here. We're looking at the how many molecules of how many proteins are converted or changed. The term is isomerized. They go from one isomer to another isomer. So how many proteins are isomerized or changed as a result of this stimulus, right? So it goes in, right, 480, 600. And remember, we've only got the one receptor type. So with this receptor type, what's going to happen is that the 480 nanometer light is going to look brighter, and it's going to look brighter because in this example here, we have isomerized 100 molecules of protein in the cone versus only 50 molecules of protein for the 600 nanometer. And the reason we isomerized twice as many proteins here than we did here is simply because that protein is more sensitive to light at around 480 nanometers. So the 480 nanometer light is going to isomerize more protein. Therefore, the perception is going to be stronger and brighter. You're going to perceive it as brighter. So even though these two lights are the exact same, physically, they're the exact same amount of light, you're going to perceive this one as brighter. You're going to perceive the 480 as brighter if you only have this one receptor, simply because that one receptor is better tuned for that particular wavelength. How can we overcome this? Well, one way we can overcome this is by simply doubling the amount of light here that's coming here. So in this bottom example, once again, we shoot 1,000 photons of light into the eye, but we make this one more intense, the 600 nanometer more intense, and shoot 2,000 photons into the eye. And what that's going to do is it's going to, once again, the 480 is going to isomerize 100 molecules, but the higher intensity is going to cause more molecules to get isomerized. Now they're still, obviously they're not as sensitive to the 480, so it takes twice as many photons to get uh, the same number of molecules isomerized in the 600 nanometer as in the 480 nanometer. And once again, remember that's because that this particular receptor that we're looking at here is sensitive to 480. It likes to isomerize at 480. So the way we push it to isomerize at 600 is by shining twice as much 600 light into the eye. Now, what the human is going to perceive in this experiment is that both lights are identical in brightness, even though physically we've got twice as much light coming out here as in here. And the reason that receptor, or the reason that person is going to perceive that as equally bright, again, is because they've only got one. This is a hypothetical experiment where this person only has one color receptor which is tuned roughly to 480 nanometers. And we simply overcame that by doubling the amount of light coming out of the 600 nanometer lamp. So I'm going to skip ahead here to this slide here entitled Monochromatism. And monochrome ants are individuals that have a very, very rare condition. It's hereditary. And basically what happens here is they don't have any cones in their retinas. They only have rods. Now, if you remember, rods are the things that perceive low light. And they're not very... the resolution that you get with rods is not very good. You're not able to perceive details very well. Monochrome ants see the world in only shades of gray and black and white. And since they only have rods, and rods aren't good at visual acuity, they really can't see details very well. So, and since all they have are rods, and if you remember, rods are sensitive to light. Their eyes are very sensitive to light. So these folks are effectively blind. I mean, they can see the world in shades of gray and whatnot, but it's pretty hard for them to function normally with this. All right, another hereditary condition that causes alterations in color perception is dichromatism. There's three types of dichromatism. One of them is called Protanopia. And it affects males mostly, about 1% of the male population, and a very few, less than 1% of females. Now, individuals that have this condition can see blue, right? So the short wavelengths are blue; they can see blue. But once they get any wavelengths above 492 nanometers, they start not being able to see any of the long wavelengths. They see yellow instead of reds. So really what they can't perceive are anything above 492 nanometers, the reds. They can really only see blues and greens and yellows, but nothing in the longer wavelength. So it seems like they're missing the pigment for the longer wavelengths. That pigment is not being produced, so they're not able to perceive those longer wavelengths. Deuteranopia affects also about 1% of males. Once again, they're able to see blue, right? They can see the short wavelengths of blue. Above a neutral point of about 498 nanometers, which is right around the same as with the Protanopia type, they see yellow, right? But what they're missing is the medium wavelength pigments. Really, they don't perceive any of the greens. Everything looks to them as yellow and blue, right? Just shades of yellow and blue because they see blue, but they perceive green as blue, and they perceive reds as yellows. Tritanopia affects very low number of males and females. Once again, individuals see the short wavelengths of blue. It affects more of a bit less of the electromagnetic spectrum, I should say, because the neutral point hits at 570 nanometers. above that neutral point, anything above that point, any wavelength greater than 570 nanometers, they perceive as red. So they see the world in shades of blue and shades of red. Probably because they're missing the pigment that codes for the short wavelength. So they don't see the greens and the different shades of green and mixtures of green and blue. So here's some examples here of what a different folks would see with this condition. Uh, Figure A, or the A. This is from your book on page two. Well, the the A here is how the world would look to protanopes. Those, again, if we go back to protanopes right here, these are the folks that see short wavelengths as blue, and their neutral point is at 492, right? Um, D is normal, right? So D is the normal one, right? And this is what it looks like to protanopes. This is what it looks like to the deuteranopes, right, that we talked about. Notice the slight variations here, right? The green. Notice how here the greens are kind of washed out because they don't have those receptors. This is how the world looks to tritianopes, right? The ones that are missing the short wavelength pigments, right? Notice how here they're not able to perceive any greens, right? So they can see blues kind of okay, but there's no green, right? Because what they have left are working together to produce all the other colors, but there's no working together to produce the green. And this is, of course, the way it looks to a normal human being. So these are the different types of color blindness that you're going to encounter in the wild, right? And once again, we have a picture of the neutral points here, right? So the neutral point for a protanope and a deuteranope, right? Notice that these guys here, their tipping point, or their neutral point, I should say, is a little bit higher in wavelength than the protanopes. And then the tritonopes are even higher still, which means that they perceive more and more of the world as blue because they're missing those, they're missing those middle receptors. And this, of course, is the wavelength for a normally sighted human being.